Two-component system is a collection of elements or components that are organized for a common purpose. A few types of liquids are miscible to each other at all measurement. For example, ethanol and water. Other liquids are miscible in other liquids at a limited proportion. For example, ether water, phenol water. Here, phenol R is not really liquid, but is considered as like that because addition of first part water decrease the melting point below room temperature to produce a liquid system. Types of solution. There are three types of solution. 1. Miscible solutions. These solutions are completely miscible at any temperature, such as a solution of water and CH3COOH. 2. Immiscible solutions. These are solutions which are not miscible with each other and not affected by temperature or any other factors, such as a solution of water and CCl4. 3. Partially miscible solutions. These solutions are miscible at a definite temperature. They are affected by temperature, such as a solution of water and phenol. Phenol and water system. One such system is phenol and water. Their miscibility depends on their relative proportions and temperature, as shown in the following diagram. Phenol and water system. The curve that separates two phases area from one phase area is called binodal curves. The maximum temperature at which the two-phase region exists is termed the critical solution temperature, or upper consolute temperature. All combinations above this temperature are completely miscible and yield one-phase liquid systems. The curve GBHCI shows the limits of temperature and concentration within which two liquid phases exist in equilibrium. The region outside this curve contains systems having but one liquid phase. The line drawn across the region containing two phases is termed a tie line. It is always parallel to the baseline in two-component systems. The curve GBHCI shows the limits of temperature and concentration within which two liquid phases exist in equilibrium. The region outside this curve contains systems having but one liquid phase. The line drawn across the region containing two phases is termed a tie line. It is always parallel to the baseline in two-component systems. All systems prepared on a tie line will separate into phases of constant composition at equilibrium. These phases are termed conjugate phases. Phase A represent water while phase B refer for phenol, because of lower density of water compared with phenol, so it will be in the upper part of the system. Phenol and water system. At equilibrium, we have two liquid phases present in the tube. The composition of 11% phenol is the lowest concentration of phenol that will form a two-phases system. Below that one system is formed. The point B represented in the figure, while the point C represent a system contains 63% phenol. Above this percentage, only one phase system will be created. To calculate the relative weights of the two phases in any point on the tie line, the following equation could be used. For example, the point D. Weight of phase A or weight of phase B equals length DC or length BD. Practical work procedure. Prepare the following concentrations. %WW of phenol and water systems, 10 g total 2%, 7%, 9%, 11%, 24%, 40%, 55%, 63%, 70% and 75%. Leave the test tubes at room temperature, 25 degrees Celsius, for 10 minutes. Then record which one has two phases and which has one phase. Repeat the work at a higher temperature of 40 degrees Celsius, 50 degrees Celsius, and 70 degrees Celsius. Practical work. Draw a curve temperature versus concentration, %WW. And show the area that contain two phases and the area that contain one phase in the curve. Draw the binodal curve. Draw a tie line for each temperature. Find the upper consolute temperature.